Good afternoon, everyone. Welcome to the RF Spectrum Sharing Challenge pitch event. It's really nice to see you all here. We typically do virtual events, so it's really a pleasure to be here in person and actually, have people to interact with. So thanks so much for taking the time to be here. And I wanted to give a quick overview of why we're doing this challenge and then what this pitch event is going to look like. So to start with, we began working with Vasu all the way back in, I think I can count back to October of 2023. Vasu had this great idea, and we worked together with him to develop a concept on how we could put this together as a prize challenge. And so in May of last year, we actually launched the prize challenge, and then from there, the finalists that you will see presenting here today have been working for 8 months, going through different rounds of testing and training with their algorithms. So they've put in a lot of time and effort, and this is our main culminating event coming out of this is this pitch event here. And so we're going to go into presentations after we hear from some of the individuals involved in this challenge, and it will be 5 minutes of presentation directly followed by 5 minutes of the panel asking some questions to those companies. And then from there, we'll have a brief pause, and then we'll announce who the winner is out of this whole challenge, and then just to close out our pitch event here today. So to start with, I want to turn the floor over to Jesse Geip. He is tuned in virtually, and he's our Venture Portfolio Director at Defense Innovation Unit. So I will turn the floor over to him.
I'm the Venture Portfolio Director with the Defense Innovation Unit, DIU. I'm excited to be speaking with you all today about the RF Spectrum Sharing Challenge that we'll be concluding with our finals today. This challenge is part of a larger effort within the Defense Innovation Unit and within the Venture Portfolio to focus on identifying new emerging capabilities developed by great companies like those represented by you all who are competing here today to help identify new and emerging solutions to some of our nation's hardest problems. So thank you for contributing your time and your skill set to this particular challenge. As we think about trying to manage comms and communications across a wide variety of different spectrum, the challenge of navigating that while we have a wide variety of systems and an increasingly contested spectrum environment for the department, both in the United States and around the world, your solutions will prove hopefully foundational in helping to solve this complex challenge. So thank you for being here today, and thank you for competing. A little bit about the Defense Innovation Unit, DIU. Defense Innovation Unit is an organization that's really focused on trying to bring in dual-use technologies into the department using a variety of creative contracting methods, understanding that some of the best capabilities that exist across our nation are not necessarily always being developed within the department, but in partnership with the department, those technologies can have meaningful national security implications. And I think this whole event really represents the best of what that is attempting to achieve. We have incredible partnerships with our colleagues from AFRL, and I want to give a special thank you to Dr. Vasu Chakravarthi for being really the brainchild behind this whole concept and helping to drive the initiative for this particular project. And I also want to thank the On-Ramp Hub team who are hosting us for this event. Their partnership in both the event logistics, the event, the coordination, and the outreach. I'm sure potentially many of the companies who applied today may have heard about the event via our On-Ramp Hub in Ohio, and we want to thank them for that. And so really today, I hope that you enjoy the event. I hope that for those who end up winning, that we thank you for developing a solution that has meaningful impact. And for those who may not win, that you continue to develop capabilities that have potentially long-term implications for the national defense of our nation. And for all of you who are attending and watching today, we hope that you enjoy the experience. And I also want to give a quick shout out to my team, Angela, Megan, Joy, Karina, and so many others within the DIU Ensign team who've helped pull this event together. Thank you for your work in driving this. And again, I'm sorry that I can't be there today, but excited to see how this event comes together, and more importantly, excited to see the capabilities that you are developed have a true impact for the warfighters that we serve. Thank you for your time, and good luck today.
Thank you, Jesse. And now I'd like to turn it over to Dr. Vasu Chakravarthi. He is a principal research engineer at AFRL, and he's the one we've been working with to develop this whole thing. So Vasu, I'll turn it over to you.
Thank you. Yeah, good afternoon. My name is Vasu Chakravarti from AFRL, has been introduced. The next 5 minutes or so, I think I'll give a brief overview of what this challenge is about and some key takeaways. This right. As you see, the whole goal of this challenge is to spur innovation in the automatic RF scene analysis or spectrum sensing and situational awareness. The goal here is the detection, characterization, and recognition is kind of the objective here, right? The solutions here can be, we said, like, hey, machine learning, signal processing, or hybrid, right? So we want to analyze like a dense, wide RF environment. We want to get kind of do more than what it's simple academic exercise. Usually analyzing a signal at a time, stuff like that. And we also know a lot of stumbling blocks, like when people are doing this thing, like low SNR, low signal to noise ratio signals, the co-channels, the multipath. We want to bring all those things into the challenge competition, and see where the community is. And this is like one of the first challenges we're doing to really see where the community is at large, to understand, come up with a baseline to see how well we are doing, where we are, understand the gaps and challenges. The goal is to accelerate and advance innovation in this area, right? So the challenge, I think the problem we modeled was even though it's a spectrum sharing model that we thought we'll take the model that's kind of community knows, which is the three-tier model you see in this picture here. We modeled this after the CBRS Citizen Band Radio System model, which has a three-tier model where the incumbent users were military users, then the person who paid for the spectrums are the primary users, and the opportunistic users are the secondary user. We took that model and adapted, and kind of, as you see in this the triangle there, the top one is like we have urgent users. They get the highest priority, and they're also the unknown users, right? I'll get to that in a second. And then next we have the medium priority, or the person like who paid. We call them primary users. And the lowest priority is the ones are the secondary users, right? So when we did this challenge, we gave the participants all the primary and secondary user signals, right? We told them what it is. Right? But we didn't tell them who the urgent signals are. They are the unknowns. Okay? So in a nutshell, how did we really get here? I think Angela said we started this. The whole thing is in May 30th, 2024. So we started with the solicitation. We received like 18 white papers. We down selected this to 10. The 10 advanced to the training phase. The training phase was like 8 weeks long, right? In the 8 weeks, we actually worked with the participant. We gave them like 3 exemplar scenes. So each one is like graduating them to go through the training process, and also AFRL guys getting trained, seeing how we should grade their signals, exchange. So I think the training process kind of set up the whole event to the next stage, right? After the training, we had the first round of testings. We call it round 3. We gave them 3 files to really test and evaluate, Then after that, we down selected to 5 finalists who are here today, right? And the final round, you see that has 2 parts again. It's like a written and orals, right? So we gave them again 3 questions, 3 files to analyze. And this morning we had they were briefing to the government team and also the stakeholders. We had over 25 to 30 government team who are very interested in this technology. They range from all these comms, radars, EW interest. So they actually had an opportunity to listen to each finalist, actually how they, behind the scenes, developed these algorithms, or how they processed it. We had a chance to see the secret sauce behind. And this actually gives us an opportunity to see, hey, if you want to transition this technology, where are they? What TRL level they are? Are they completely like a bench level man in the loop processing, or how close are they to automatic, right? So we want to, at the end of the day, transition this technology to the warfighters. So I think we had a very good chance to see where they are. we're extremely happy with the whole outcome of the, how this whole thing went, how the technology solutions, what they provided. Finally, key takeaways. Again, like I said, I have 5 minutes. I want to make sure I keep to that. If you want to remember this whole spectrum challenge in a nutshell, just remember the game we played is spectrum sharing, right? The challenge within the game is spectrum sensing, and our objective is to spur innovation in signal processing, machine learning, and also, most importantly, I kind of missed it saying, how do you generate the training data? I think we kind of changed the philosophy here in this challenge of the participants generating their own training data, right? This is actually, we're pushing this different philosophy here. So that's kind of in a nutshell what the game is about. Of course, the benefits of doing this thing, it's going to benefit both commercial and DoD, right? Applications, the comms, radars, EW. And most importantly, I think the spectrum situational awareness is key to spectrum management for the DoD guys, or we call it EMBM, electromagnetic battle management, other name, right? So eventually, I think the spectrum challenge is going to help us develop and evaluate dynamic spectrum access and spectrum sharing concepts and technologies, which I think OUSD is very interested in these things, right? That's all. Thank you.
Thanks, Vasu. And next, I would like to introduce Scott Fox. He is also going to participate as a panelist here for the Q&A portion. And he works with OUSD R&E, Future G. Sir, if you'd like to come up and say a few words.
Thank you very much. Well, it's been a pleasure observing the activities over the last day, and I really appreciate all the hard work there. I just wanted to share just 1 minute on Future G, right? So I work for DoD, OUSD, R&E, Future G, right? We're focused on applying commercial technologies in ways that benefit the warfighter, right? And we're doing so by minimally modifying to achieve the desired outcome. So much like DIU, everything we look at, we really want to have a dual use purpose so that the commercial industry continues to support it, develop it, pound on it, add resiliency to it. And we're not dependent on evolving it over time, paying for every little feature and not pounding the heck out of it, right? There's many reasons. So we live in this dual use world. And so you might hear some questions coming from me. It also, for many of you who haven't who aren't focused on this, could allow you multiple revenue sources as small companies too. There's two different approaches to getting revenue, and often the government's early on is beneficial early on. You might transition to commercial, but certainly there's many opportunities, including public safety, right? So I just wanted to share that. My background is 40 years on the commercial wireless side. I was a chief technology officer of numerous companies. I represented the mobile operators around the world as chairman of the GSM Association. I led the FirstNet team designing our nation's first generation broadband network for first responders, and I've spent the last 4 years passionately focusing on and dealing with our warfighters, right? And I spend most of my time outward facing to the industry. So we're seeking solutions, and we've spent a lot of money on research, large scale prototypes and small research programs. So very excited to hear. I just wanted to share my personal perspective, what I'm looking for. As Vasu said, as a nation, right, we are challenged with spectrum, with having available spectrum for DoD, constant pressure from the commercial industry who has a ton of money, right? And we have to be able to defend that, right? So we not only need a solution that gives us spectral awareness and flexibility and agility. We need frameworks to be able to live within this dynamic spectrum sharing. And additionally, though, we need the commercial world. Our group needs the commercial world to buy into it, because we're going to be sharing spectrum as a nation with the commercial world. And it's part of the reason I'm mentioning the dual use here, because from my perspective, the vast majority of this, some will be used internal to the DoD, but a lot of it needs to be outward facing so that we can collaboratively share spectrum with the commercial world. So thank you.
Thanks so much, Scott. All right, and next I would like to introduce John Owen. He is a part of the Defense Innovation On-Ramp Hub here in Ohio. And so, John, I'd like to turn it over to you so you can speak.
Thank you. I get the honor to welcome everyone to Dayton, Ohio. Thank you for those teams that traveled in from out of state. We're happy to have you here. As Angela mentioned, I'm from the Defense Innovation On-Ramp Hub, Ohio. At the On-Ramp Hub, Ohio, we provide mission-focused problem solving, access for Ohio companies to DIU programming, technology assessment, and then we also offer a physical presence here in the state of Ohio to host things like this, bring people in from out of state to meet with our partners like AFRL at a larger scale level. But we could also offer kind of one-on-one meeting spaces as well. So if a mission partner wants to have a kickoff meeting with a new client, we can host those type of events here too. Again, welcome everyone to Dayton. Excited to have you here, and best of luck to the participants today.
Thank you, John. So we are going to start with our first presenter. We have Syncopated Engineering. So they're going to come on up, and
Hi, my name is Jim Costable. I am with Syncopated Engineering. I'm the CEO and founder, and I'm here with John Voorhees, one of our senior DSP engineers. We're a cognitive radio company out of Baltimore, Maryland, and we're known for our ability to sort of commercialize our research and development as evidenced by our Cielo cognitive radio product line, which has resulted in multiple commercial products. We embrace dual-use technologies, but also while trying to make sure that we have the ability to make them purpose-built for the unique and dynamic military mission. Problem statement's already been over, but what I really wanted to call attention to was the primary and secondary signals are very close. Their modulations are close, their features are close, so it's not easy to tell the two of them apart. The new part in this is the urgent users. So these are unknown users, these are unknown signals, numbers of signals, types of signals, and they have a time element to it where you have to detect how long they've been active before they lose their priority. So here's our technical approach. It's a hybrid mixture between cyclostationary signal processing and deep learning machine learning. Our signal detection and isolation is primarily signal processing with the ability to separate the wideband into narrowband channels, isolate and energy detect those channels, cluster them together into a signal representation, and then through a simple and computationally efficient frequency filtering, isolate them and create a perfect reconstruction system signal that can then be pushed to the classifier. The classifier, the next block down there, starts with feature maps that are built on cyclostationary signal processing. It uses both the cyclic correlation and the spectrum correlation, exploiting known features, but also working to do a more generic version that'll capture the unknown features of those urgent signals, stacking them all together in an image, and that image then goes to the signal classifier. The signal classifier is a deep learning model, and it allows you to go in and both classify the type of signal and also the user. Being able to do both the class of the signal and the user type for us turned out to be much more beneficial than just doing the user alone or the signal alone. Finally, those results, those classification results, go to a decision engine, and that decision engine determines the ability to transmit and the spectral occupancy map of all the different user types. Here's an example of our feature maps. As I said, we used on the order of 75 features, each a row in this image, and they were all 256 pixels or frequency bins wide. So you can look at this feature map and see the different features, and just through the eye you can see how some of them are discriminated from the others. This is what fed our deep learning classifier. This slide just kind of captures how some of the work that we did today is commercially viable. On the left side there, you see Hornet, which is our distributed collaboration and geolocation. You can have distributed spectral sensing. The algorithms we did today, we can implement on that device. Mockingbird is a software-defined test system currently on the GSA schedule that allows you to build those complex, rich RF scenes that enable you to do some of these RF machine learning things without having to have all the storage of the massive data sets you need. And that's us from Syncopated Engineering. Thank you very much.
to turn it over. I think I can leave this with you. Sorry, you're our first one. Turn it over to the judging panel to go ahead and start with
My
their
turn
Q&A.
first. Very nice briefing. Good work. What aspects of the challenge you guys really enjoyed? It's 8-month long work. You guys did fantastic work. What aspects of the challenge you were like, oh my God, no? What was the best parts and worst parts of the challenge?
I really think the best part of the challenge was the ability to get in the game quickly. So we've been in some of these before, and it takes a lot of work to sometimes get to the starting line. But with this one, with the data sets, the way they were generated, the way they were used, the same tools and we were familiar with, enabled us to start running right away. So that was awesome. The challenge is always time. We're a small business, and so how you find enough time pulling away from funded customers to do this kind of work that you know is amazing and you can't wait to dig into. So that's one of the bigger challenges.
Thanks so much for the presentation. You mentioned on your first slide some of your existing commercial products. Can you elaborate more on who some of your commercial partners are?
Sure. So Mockingbird is probably the best one to show off. That is just a commercial piece of test equipment, software defined. So it's on the GSA schedule, but people can buy it that are, developers or in the government, outside of the government. It's just a very flexible software defined test system for wireless engineers.
Thank you. Great work that you've endured and survived and exceeded, right? So fantastic. I wonder if you could just comment on what were the one or two things that encouraged you to participate here? What drove you here? Was it the competition? Was it the learning you might get out of it? Was it you felt it would move your business along? I'd be curious to hear, and did you achieve that as an outcome?
Thank you. Yes. So we've have experience in many of the things that were part of this challenge, not always mixed together. So we had machine learning capabilities, we had cyclostationary capabilities, and we didn't have a good opportunity to put them together. So one of the things that got us excited about this was putting it together. The other thing that got us excited about this was both comms and radar signals. So that was also sort of a unique aspect that was encouraging, right? And then we were excited to kind of refresh each of those individual disciplines as we were putting them together and take on some things, in particular the very low frequency repetitive things that we hadn't solved that problem yet. So we were pretty happy with this result that we were able to extend our research capabilities in that area.
Do we have time for me?
Yeah, sure.
Hey, Syncopated. I was wondering, is the complexity of your solution more on the inference side or the training side?
Yeah, so as far as computational complexity is concerned, the largest part is the cyclostationary feature generation. So generating each row of that feature map image you saw is computationally intensive. So and we did that kind of all in MATLAB right now. So there's a lot of optimization we could do to try to bring that compute time down. But yeah, that's the most expensive part.
Thank you.
All right, is that it for questions? Anything else? All right, well, thank you so much.
Thank you.
All right, next up we have Aeronaculus.
So my name is Dr. Apurva Modi. I'm the founder and CEO of Aeronaculus. First of all, I'd like to thank Ensign, Dr. Vasu Chakravarti, Chad Spooner, Scott, and others, and Megan on the team for amazing work to get us to this point. Aeronaculus is a startup company. We are located in Boston, and we are doing something called as autonomous intelligent reconfiguration. It is nothing but a self-driving technology. We call it self-driving technology for heterogeneous wireless networks. It's a NASA-funded technology that provides 10x improvement in communications quality. We have a world-recognized team that has got people with successful commercial exits, as well as track record of government business execution, government program execution. I'm a fellow of the IEEE. I was formerly the vice chair and chair of the National Spectrum Consortium. I have 25 plus patents and pretty well recognized in the area, in the field of communications. Brian Crompton over here, he is the primary person who worked on this NSYN RF Spectrum Sharing Challenge, along with Daniel Geiger on our team. So Aeronaculus is a company since 2019. We've done about $15 million in business with the government. NASA is one of our main customers, but we have many other customers. Our revenues in 2023 were $2.8 million. We have applied for we've been granted 2 patents, and we applied for 10 patents, so we are really an innovative company. We have raised $1.7 million so far from investors. So our investors include Harvard Business School alumni angels of New York, also some other larger defense corporations and high net worth individuals. We are planning to go to the seed round this year sometime. So hopefully that happens, and basically we'll be launching our several commercial products as a result of that. So we are about 15 employees, and we are working on go-to-market strategies, especially in the area of 5G, with companies such as NVIDIA, Radisys, Lockheed Martin, and others. Some of the core thrust areas that Aeronaculus works on is signal-on-signal detection and characterization, robust and resilient wireless communications, spectrum sharing. So spectrum sharing is one of our fortes, as well as we've made a recent foray into smart wearables. So we are doing a lot of machine learning and data analytics on the data that is coming from smart wearables. So all in all, the core thrust area is AI RAN, or artificial intelligence for radio access networks. We have had a very successful track record in government business. So as you can see, these are some of the programs that I've highlighted, especially in the area of signal-on-signal detection and characterization. And these slides are available, so you can take a look at them. So just to give you a little bit of insight into what our approach was for this particular NSYN Spectrum Sharing Challenge. So the core approach was, the first thing was segmentation and extraction of the signals. The second thing was extraction of the features. The third thing was decision making, and the fourth thing was assembly, so that we could provide the results. And all our past programs that I talked about, they really helped us in getting to this particular point. So as you can see, our entire focus was generating rich features, right? So going from power spectral density to spectrograms, waterfall plots, autocorrelation, cyclostationary signal processing, which consists of non-conjugate as well as conjugate cycle frequencies. And all that resulted in the decision of what the signal was. And based on that, we could recognize whether it was a primary user or secondary user or urgent user. And then based on that, we were able to make a decision on spectrum sharing. So these are some of the examples that show you that just based on cyclostationary features, you can recognize various signal types. For example, primary user phase shift keying signal at 1 megahertz of bandwidth, or secondary user signal, or direct sequence spread spectrum, or even an urgent user system. So our classifiers basically made extensive use of statistical signal processing. We as a company do a lot of machine learning. We do feature-based machine learning. We use deep neural networks. We use multimodal fusion. We use image processing. The two things that we used in this particular challenge were statistical signal processing and image processing. So those were the things that we used. But in future, we plan to use RF machine learning also. So all in all, Aeronaculus, we are trying to actually optimize not just the physical layer, but cross-layer, right? So we want to our core thrust is to optimize a heterogeneous wireless network. We are providing a platform-agnostic solution that makes all commercial as well as military radios robust and resilient to interference and congestion. And so most of the core, core capabilities is interference and congestion mitigation, AI-enabled network optimization, spectrum situational awareness, and API-based integration, for example, into ORAN. So that's what we are developing, this solution. Okay, thank you so much for everything, and we really enjoyed working on this challenge.
Great, thank you. Very, very good. Great overview. I'd love, do you have any specific examples of the key learnings that you're taking away from this in terms of how that'll benefit your products in the marketplace? I know that there's the competition, there's a lot of recognition, there's hopefully some money, little money But I'm curious how it might have informed or influenced your product set.
Yeah, so I think one of the core thrust areas for us is signal and signal detection and characterization. So, for example, we've been having discussions with several commercial companies. If you look at this entire space, for example, Legato, right? Legato is trying to have their 5G systems right next to the GPS. Interference is the biggest concern, and that was one of the reasons why Legato is again going into bankruptcy and restructuring, right? So interference is an issue that keeps coming up all the time. That's a very, very important issue. Whether you look at the licensed spectrum or you look at unlicensed spectrum, they both have interference issues. And I think that this is a core area where we need more insight, right? So this challenge actually, especially all this complicated scenes that Chad created here, that has really helped us, and it has actually helped our understanding of what we should do for signal processing to make the decisions better.
Thanks so much, Apurva and Aeronaculus team for the presentation. I'm just curious, can you talk about a time potentially where you had to shift your approach in, characterizing and identifying the signals throughout this challenge?
Yeah, so we started off with a hybrid approach where we're going to generate all this data, but there are just too many details to keep track of in generating the data set. And we saw that we could get better marginal returns with signal processing.
Chad wants to ask, or?
Yeah, I'll ask. Hi, Aeronaculus. I was just wondering if you could tell us one interesting thing that you learned in this challenge about signal processing, or machine learning, your choice.
So I enjoyed discovering the urgent user constellations. So discovering what the urgent users were was kind of fun.
Thank you.
Is it my turn? Okay, we have 3 aspects of this challenge, right? Detection, characterization, and recognition. Now, since the challenge is over, you got evaluations, how well you did. How well you think you did on these 3? And where do you think you need improvements? And what's your plan? How are you going to improve this?
Yeah, I think first of all, we've learned a great deal. I will let Brian answer some of the technical questions, but just in terms of we were able to take a lot of the core pieces that he had. Like for example, we had modules that did cyclostationary signal processing using SSCA, which we had converted to GPU, we had accelerated using GPU, image processing modules, autocorrelation modules, other modules for image processing. This challenge actually helped us to bring all of them together. So that was very important. Where we are going from now is that I think there are a lot of customers, potentially you guys and Army and others, they're looking. In fact, we were just told today that we might have won another program with the Army, which is to do with signals and dataset generation. So that's a direct to phase 2, which is really awesome. And so there are a lot of programs and a lot of customers who are looking for this capability. We would like to keep improving this, putting more resources into this, not just in terms of funding, but also in terms of computational resources, make things faster, make things more streamlined, and then have a complete product, right? So that's what we are aiming for as a result of this. And Brian, I don't know if you want to answer.
I don't recall the question.
All right.
We are just about at time, so I just want to say thank you both. And we'll go ahead and go on to the next one. All right, so next up we have Expedition Technology.
Yes, thanks for having us, everyone. My name is Ryan Crawford. I'm here with Josh Fitzpatrick. We're representing Expedition Technology. And again, appreciate Vasu and everybody for running the program. It's been a fun challenge. So we'll talk about our solution today. So first, just about Expedition Technology, what do? We do a lot of RF signal processing, so that's kind of the top right box here. Half the company from emitter association, so like fingerprinting or SEI. We do anomaly detection, and then we do a lot of this RF spectrum awareness, very similar to how this competition works. But we also have a large part of our company who works on GeoInt and computer vision, probably the other half of the company. And then we have a very large program where we do foundational AI, AI, ML, like data set management. So we have a tool that hosts a large amount of labeled imagery. And you can go in and select, I want to see all the imagery that's been labeled for this object. That's a very successful program. And so we have a lot of experience on, both the more traditional ML side of computer vision, that's a lot more mature. And we're using all the lessons we've learned as a company there to push into the RF that's a little bit newer, I would say, and less mature. Next slide. And so for this program, we had a very automated, solution pipeline that relied on a lot of ML and just a little bit of traditional DSP. So we were able to take in the wideband RF scenes that were generated, feed that into what we called our wideband signal detector that tried to localize all the signals in the environment. And then we split that into two narrowband processing pipelines. One was a narrowband signal characterization network that was a deep learning neural network that tried to detect the modulation of the signals. And then we did a little bit of traditional signal processing to estimate the symbol rate and frame rate of the signals, and then use those results to generate our share matrices. Next slide. So those two blocks, in more detail, that wideband network, that's the idea of where, given a whole scene, where are the signals? We want to estimate the bounding boxes of every signal. So we're training on randomly generated scenes of mixed signals of the PUs, the SUs, and then our just imagination of what the UUs might be. And then for the narrowband network, we're training on individual scenes. So we've assumed that the wideband thing has localized the signal, and then we're going to feed in just that localized signal that's been channelized out of the scene and try to estimate what the modulation of that signal is. For the wideband network, we have something we developed under the DARPA RIFML program that we call the multi-scale spectral UNet architecture. So it's a fully convolutional neural network. One of the neat things here is it takes in a spectrogram. As long as when you train, you don't change your FFT size or basically your FFT resolution, you can actually train at one sample rate and then run evaluations at a different sample rate. So maybe you have data collected off of one SDR at a certain bandwidth. You can use that data to train and then actually run this network for inference in the field at a different sample rate, which can be very nice for computational reasons, but you can train at a low sample rate and then deploy at a very high sample rate. It's very useful in that sense. Next. We had a narrowband modulation recognition network that we worked with, with Dr. Chad Spooner. It was inspired by cyclostationary features, so we've seen a lot of the other teams talk about using cyclostationary signal processing directly. We sort of sidestepped that a little bit, and we used some novel input representations to feed the neural network, where we raise basically the data to higher orders and pass that into the network in both the IQ and in the FFT domain. And the network's able to leverage that, those different orders of representation to learn similar things that you would get out of CSP, but actually with a lot lower computational cost. Next slide. And then we have an extensive simulation capability where we can create scenes of the SUs, the PUs, the UUs, where we had a lot of real-world impairments. So it could be receiver front end, things like clock spurs, multipath, all these sort of things. A lot of the stuff in this particular challenge was simulated, but in the real world, if you want your neural networks to actually translate, you want to have this kind of stuff for them to work, on multiple SDRs, not just the one they were trained from. Next slide. And then all of that, we're able to stream this dynamically. So we can generate these scenes on the fly during training. So during training of the neural networks, we're actually generating essentially infinite random draws from these distributions that we've defined. So instead of having a static data set where you either have to store a lot of data on disk or hope you made enough data, we can continuously generate new draws from the data set. And if we just want to tweak something for a new run, we just change some hyperparameters, rerun again, and you get a whole new data set for that model. Next slide. Then our final pipeline. So we would take in a wideband spectrum on the left. The first network is going to define these bounding boxes of where it thinks all the signals are. Then we feed all those bounding boxes into the characterization network, and then it's going to attempt to output whether it thinks it's an SU, PU, or UU, and then we'll generate finally the ability to transmit result. And that is it. Next slide. I think that's it. Yeah. And so take questions.
You're one of the few that actually was more machine learning than signal processing. And one of the philosophies we were trying to push in this challenge was on the focus on the data generation, the training data. Instead of a customary way of, what do you call it? The host giving you the data, we are asking you guys to generate your own data,
Yes.
right? So how did you really go about generating your own data, with the information we gave, and what are the challenges there?
Yeah, so for the comm signals, we already had in our WaveGen simulation, I guess, pipeline, a very easy way to say if you said it was a BPSK with a symbol rate, some frame rate stuff, we could define that very easily, generate, on-the-fly instances of those. For the radar signals, we had to add some new blocks for some of that, and we had to, I guess, parse the data set a little more precisely to understand what those were, since they weren't as clear, they weren't as specifically defined exactly what they are. But we had a lot of stuff off the shelf that made it pretty easy for us to just generate these scenes readily.
So the exemplars we provided, or the the different looks of the signal,
Yep.
was that helpful? Or?
It was. So we would use what we did specifically was we took our WaveGen, I read the specification, generated examples from WaveGen, and then plotted like the PSD and a spectrogram of both signals side by side, and made sure they kind of look the same, and then checked constellations. And once we were like, okay, our WaveGen's making exactly like the exemplars, then we went from there.
So the difficult part of this thing is the urgent user, the unknowns.
Yes.
So how did you account that in the training?
Yeah, so we just assumed that by definition, if it wasn't an SU or a PU, then it was a UU. And so during training for that narrowband modulation network, it's essentially a generic modulation recognition network. It's attempting to understand, if it's, it doesn't have to just be the subset of modulations that were in the challenge. We have other ones that we can generate. So we're just generating random examples. That doesn't really care that it was an SU, a PU, a UU. It's just telling us what it thinks the modulation is. So that's pretty generic. Then we just paired, once we had what modulation we think it is, and our symbol rate estimate and frame rate estimate, then I think it's a PU, an SU, or a UU. But that was pretty straightforward for our pipeline.
Thank you. Very good.
If you had some more time with this challenge, what aspects of your solution would you have worked to improve?
We would have used a little more signal processing, is the truth. So I think some of the way some of the signals were defined definitely made it more easy to just do signal processing. And I think as a company, we do a lot of machine learning, but we try to not treat it as just like we have a hammer, we'll do everything with machine learning. There's some things where if someone gives you a very specific DSSS definition, just use signal processing. You don't need to waste a bunch of flops with a neural network. And so we try, when we're doing more general solutions, we try to use as much DSP as we can and only use the ML where it's actually helpful. So something like ModRec, I think the deep learning is nice. For a lot of the other stuff, the DSP is better.
Thank you. I think one of the benefits you got was you looked more automated, right? Which was a feature, at least at one level, right? So I like that. One of my passions and areas of responsibility is workforce development. One of the reasons I'm here, right? So I'd love your perspective on the level of this material. Do you feel that it's appropriate for graduate level work, or where do you think it would fit into an academic scheme? Is it appropriate in the at that level?
I think a strong grad student possibly could handle a lot of the comm signals. I think you get less EW experience, so the radar signals might be a little trickier. But some of the basic comm signals I think are pretty straightforward, and a graduate student will be able to tackle that pretty well, I think.
Great.
Yeah.
Thank you very much. Thank you.
Chad, you got anything?
No, I'm good. We should move on, I think.
Thank you, Chad.
You're welcome.
Thank you so much. So next up, we have Alpine Technologies. Excuse me, Alpine Method Technologies. Let me get your slides up.
Good afternoon, everyone. Thank you for hosting this event. My name is Michael Zolkowski, and this is James Letendre. We're with Alpine Method Technologies, and we're going to talk about how we adapted Spectral Terron to meet the needs of this competition. Spectral Terron is a phase 2 small business innovation and research technology that is intended to automate the process of blind spectrum situational assessment. Spectral Terron is like having a digital canine unit to patrol the RF spectrum with you. And specifically, it's a software that guides operators through the monitoring and research of signals. It's a combination of advanced cyclostationary signal processing and machine learning. And to talk about some of the technical approach for this competition, I'm going to hand it over to James.
Hi. So like most of the teams, we utilized cyclostationary signal processing for a lot of our modulation recognition stuff. Our spectral Terron project focused mainly on comm signals. So for this challenge, we had to kind of stand up our radar processing flows. So we really utilize things like autocorrelations and peak finders and stuff to find those radar pulses. Our solution is mostly an automated one. We feed our data through kind of the two parallel pipelines that we set up, one for comms going through our kind of cyclostationary signal processing approach, and one for the radar signals. Those kind of merge in together at the end once we've done all the classification of which signal type it is, all the parameter estimation for symbol rates and things. We then make those determinations of which signal class, the urgent, primary, or secondary users, and meld all that together into our matrices that we then would submit for the scenes. And that's all we've got for this. Do we have any questions?
I can go first this time if that's okay.
Sure.
Okay, so I have two questions. First one is, why did you call it spectral Terron?
We have some small children with lots of toy dinosaurs at home to serve as inspiration, but a pteranodon is surveying the lands, provides you a wide and broad understanding, and that's what spectral Terron is able to do. It's able to soar above the spectrum and provide you some novel insights.
So you want to see everything, right?
That's right.
So, so on that note, then pretty much all the scenes I made had very, very few low SNR, noise floor or below signals. So a lot of the teams, everybody got away with, energy detection, right? What happens if you're trying to use spectral Terron to get at a signal that's below the noise?
Primarily we use energy detect to figure out where energy is to focus our CSP processing, so you can kind of reduce some of that computational load. But we can, flip it around and look where there isn't energy to try to find stuff that is below the noise floor, and try to extract some of those signals I might be trying to hide, or be, just lost in the noise because there's just very low SNR.
Thank you.
In your block diagram, you had like a path for comms, path for signal, radar, right? And you're more automatic than manual, or what aspects of it's manual? The reason I'm asking is, how did you segment your signal? Because you're taking IQ, how do you know it needs to go to the radar path or comms path?
Yeah, so we ended up teeing the input and sending all the same IQ data to both.
Oh, both.
Yep, and it was 100% automated. And then at the end, we had decision logic for that merging at the end, which allowed us to produce the single, matrices for the competition.
So what happens if you're sending the IQ to both comms and radars? What happens to the comms when it sees a radar signal or vice versa?
We kind of do some kind of deconfliction there. So with the radars, they kind of show up in CSP as not looking like any of the kind of comm signals, and because they're very narrow, generally for the radar stuff, or characteristic of like our radar stuff finds it, we kind of go, okay, I don't think it's this thing that our CSP stuff was saying. It's probably the radar. Or if we find a radar where there was a good comm signal detection from our comms flow, then we defer to that one. So there was some logic to figure out which of the two we should trust for the decisions when there were kind of two in the same spot.
So where I'm going with this is automatic inside each block. If it's manually, I can tell that, oh, okay, a comm signal is going down, maybe ignore this, put a threshold or something manually. Where I'm curious is, how did the whole automatic thresholding say, like, hey, the comm signals goes into the radar. Right now, if I put a lot of comm signals in our radar ES, it's going to really create a mess. Right? That's why I'm curious to see, how did you actually block that automatically?
Yeah, so like we show that as like the teeing off, but we tended to run the comms first, which would tell us where we think there's actually like good comm signal blocks, and that would then feed into the radar to kind of block off things of like, don't look here, we think this is a comm signal. But we did, just the dedupes of, if we got a good detect from our comms, we didn't like focus there for the radar stuff. The assumption being that they wouldn't overlap radar with a comms in any of the scenes.
Okay.
Can you tell us where Spectral Terron's at in its development? What's the TRL, and are you at a point where it can support real-time processing?
Yeah, thanks for that question. So we designed Spectral Terron to operate in a 24/7 real-time processing type of mode, which is important because the way that you design a system is going to be different if you're intending to process in real time for continuous amounts of time versus like a post-processing. So we designed it to operate in real time. And in terms of the TRL level, the SBIR program for phase 2 is where you work directly with the end user and you build a prototype that they can get hands-on with their data. So we were able to successfully do that with our end users, really focus on product mission fit, and we're really excited about the traction that we're getting moving forward.
It's great. I really liked your presentation and your approach as well. A number of us were looking specifically for innovation across the teams in the area of co-channel interference, right? Co-channel. I'm wondering what, and I didn't see a lot of that, didn't see much of that. And so I'm wondering if I missed some of that, but more specifically, what are your comments about how your ability to deal with co-channel and any unique approaches to that?
Do you want to talk about the pilot tones?
Yeah, so like CSP has some ability where you can kind of find those co-channel things. So you're able to kind of leverage some of that, but we did have some difficulties coming from like the spread spectrum signals. Those made it harder to pull out your underlying ones. I think that's an area that we definitely could put more improvements into to get better results from like those sorts of interferences. But we were able to do pretty well with the, when it was PSKs on PSKs or more simple co-channel interference type cases. Thank you.
All right, thank you very much.
All right, and last but not least, we have Georgia Tech Research Institute.
All right, so hi everyone, thank you for being here today. My name is Shweta, I'm a research engineer at the Georgia Tech Research Institute, and I'll be presenting on GTRI's approach to the RF Shared Spectrum Challenge. I'd again like to thank the organizers for putting together this awesome event. I've been learning a lot through the process of preparing for this, and it's been great to hear from all the other competitors as well. So with that, let's get started. Yes, that goes forward. So one of the key motivators for GTRI to join this contest was actually the ability to develop our simulation environment. And so this figure on the right represents the scene that we were able to create. So we have frequency on the y-axis and time on the x-axis. So here's like our 1 second exemplar scene, sort of like an exemplar scene, the one that we were able to create. And we built this to be scalable to new emitter definitions and different types of channels. So not only can we create scenes that are mapping to primary, secondary user types or urgent or whatnot, but it's a little more we're able to expand beyond that. And the way we did that was by integrating with our existing GTRI high fidelity simulation environment, Aspen. So this is something that we've been developing for a while. It primarily started out as a program to work on space-time adaptive processing, but then it's moved more into the ability to generate a radar data cube. And so for this challenge, we then also had to add in the capability of adding these communications types of signals. So we were kind of coming at this with a stronger radar background. And in developing, when I'm talking about Aspen, I should also mention that we have our Angry Kitten system, which is an electronic support system for electronic warfare awareness. So this is a system that we've developed and worked with DoD sponsors on. So this is something that this plugs into that. In terms of actually validating how well our simulation environment worked, we tried to validate it using automatic modulation classification approaches. So we were concerned that maybe the data that we're generating might be a little different than data that we would get from other sources like the challenge. So to get a look into that, we used an AMC. So we trained it on data that we generated, and we ended up testing it using the exemplar signals with noise and other artifacts introduced, and we found that we were still able to perform this automatic modulation classification. So that way we were able to verify our ability to generate these comm signals, which was something that was a little bit different for us for this challenge. In terms of an overview of what our system actually looked like, I'll go through this block diagram really briefly. We take the signal, we apply our polyphase filter bank to it to channelize it. We then apply an energy detection and we do our coarse detection there. We did consider some other options, but ultimately we stuck with the energy detection. We then cluster our signal from the subepics into clusters of here's a region that we want to process all together. Occasionally, sometimes you would find that signals were right next to each other in time. So then we did need a way to temporally split up the signals. So we would look at those clustered signals and break them up temporally and take a look at where there might be some sort of energy or power level change and draw a boundary there. From there, we move on to first doing our pulse detection. So again, very radar focused. We're trying to see where the pulses are, their time of arrival. We're trying to see their pulse amplitude. And save all that information off. And then within that waveform, if we see multiple pulses, then we want to record what that pulse repetition frequency was. And then at this point, we can also perform a header search, which essentially is helping us see, like, is it some sort of communication signal? And then once we have all this information about all of these different segments, we're able to move on to the emitter classification, which was essentially applying all the spectrum rules that were given to us from the challenge. So this is something that can be modified. So if we had a different definition of like what a primary or secondary user might look like, we'd be able to handle that by changing how we sort all of these different things. So we'd be able to sort out for a different definition, whether it's a primary, secondary, or urgent user. So one of the key takeaways here from this design that we went with, it's this very modular design. So we'd be able to like slot in a machine learning solution later on if that was something that we wanted to do. And because we were working extensively on this data generation, we were thinking initially of doing a more hybrid signal processing machine learning approach. But ultimately, we fell back to that more pure signal processing method because it allows us to baseline how we expect things to perform. And then we can add in machine learning as needed and see how it improves upon this baseline. And one other thing is that since we have experience implementing these blocks in like real systems for customers, we know that this is something that can be implemented to run well on a real system for real users, whether it be for a DoD application or something outside of that. And I believe I'm at the top of my time, and that is all the slides we have. Thank you.
Thank you so much. I'm just curious if you could speak more to your role within GTRI, how you got into this research, your partnership with Dr. Reed, I believe that's his name.
Yes, so Dr. Reed, he might be listening online from where he is right now, but I actually started working at GTRI in October, and that's obviously after this contest started, so I've been very quickly onboarded onto this project. I've been looking through his code base and really learning about all the different aspects of it, and it's been a great time. So I personally am new to radar, GTRI obviously is not.
Hey, Chad, you want to ask a question? You might have a question, I thought.
Yeah, sure. Hi. You might have touched on this a little bit, but suppose there was a new PU signal that was added to the sharing system. In the context of the system that you used here, how easy would it be to add that new signal to your system? And do you think that could be automated somehow for an end user?
So the way it works right now, we would have to like add that definition essentially to our lookup table. So we're looking for radar signals, but we're not necessarily just like throwing away information if it didn't like match the PRI or pulse amplitudes that we were expecting from the definitions. We still have all of that information saved, so we'd have to like add in that definition to our dictionary when we're doing that final check of assigning it to PU, SU, or urgent user. In terms of automating it for an end user, I'm not sure I can speak to that, but I think some of the stuff I said does get at how it would be relatively easy to add it to the dictionary.
Thank you.
I think I got a couple of questions actually. One maybe I'll start with, because Jeremy said earlier he was actually building the whole simulator just for this project, right? It was pretty impressive. Somebody actually builds the whole simulator training for this project. It successfully. So you guys, did Jeremy actually implement all the signals we had in the participant document into the simulator already?
Yeah, so the way the simulator works is that we have this code base called Aspen, and then we're essentially like extending from that Aspen class, if you will pardon my object-oriented speak, and we can define different emitters based on that. So we have like a different definition for all of the emitters defined by the contest, and it wouldn't be difficult to then define more within that realm of a comms or a radar signal.
So we were heavy comms in this than radar, but you guys GTRI is more radar than comms. So what are your plans on now adding more complex radar signals? Did Jeremy share any of this with you yet?
Not yet, but I'm sure he has plenty of ideas on how to make the radar data generation a little more like realistic to like all the different nuances that you would have in like a real system if you were trying to collect radar data.
I asked this question because you said he's listening somewhere. I was hoping you'd answer.
He might be. I'm not sure if he was able to join, but he said he might.
Right. And another very interesting aspect is most people here start with comms. Everybody's radar is very challenging. But you guys started the radar. But what I see fascinating is you're using the same signal processing to do radar and comms. How did you handle comm signals in your radar processing?
So what ends up happening is that we did start with like a very radar, like it looks like a radar processing chain, but we're essentially just adding in an extra check for headers. So once we find those headers, we can figure out the block lengths and the header lengths and all that, and then we're able to match it to the emitters. So essentially it just happens at that sort of last stage where it's like we've done all the checks for radar, maybe we saw some radar signals in there, maybe we didn't, but we're also going to look for headers. So the real thing was the header check.
So inside after the segmentation and everything, you know how to identify radar signals, but you also have checks for comm signals.
Essentially, yes.
Okay, got it. Thank you.
Yep.
Thanks. Just a quick question. Do you, maybe the same question on the co-channel, right? Do you have an observation about how you were able to deal with co-channel, or did you come up with any innovations to help you achieve that?
I'm not sure that I can speak to that specifically, but I can definitely ask Jeremy to get some more insight on what thoughts he had on dealing with the co-channel situation versus single channel, because most of the stuff we did here was focused on single channel, yes. Yeah, thank you.
Thank you. All right. It was great to hear all of the presentations. I hope you all learned a little bit more and you enjoyed learning more about those proposals and their solutions that they've offered in this competition. I wanted to go ahead and announce the winner of this challenge, and this was, as I mentioned before, it was an 8-month process, so it's not just today that they were scored and determined a winner. It's been ongoing. It's been a lot of hard work as far as the finalists who have been involved. And so the top performing company coming out of this challenge is Airnaculus. So I'd like to invite you up to say a few words. Let's give them a round of applause. And thanks so much to all of you for all of the time and effort you've put in, because I know this was a lot, but I'd like to have you share a few words. So,
Thank you so much. Actually, thanks to Ensign, Air Force Research Lab, like, all your contractors and Chad, others, for putting this together. Very complicated scenes. And we are humbled, to tell you the truth. We've been in top of the competitions many times, but we've never won. So this is the first one for us. So really appreciate it. And this is the motivation for us to do better. And actually what I see, especially with all the competitors, is that we all have something. So maybe we all come together and it is possible for us to combine and join forces and provide some amazing capability to the US government and the DoD. So I think that that's what we would be looking for.
Great, thank you. All right, and from here, I wanted to go ahead and introduce Megan Saunders. She is one of the Challenge Program Managers, and she's going to go ahead and close this out today.
Thank you, Angela, and thank you all for taking the time to be here with us today. We know your time is extremely valuable, so we do appreciate the attendance for this all-day event. I also wanted to extend a huge thank you to John Owen and the entire Hub team here at the Defense Innovation On-Ramp Hub, Ohio, for putting on a truly spectacular event and for all your help in coordination. I also just want to take a moment to highlight the great partnership with Dr. Chakravarthy and Air Force Research Lab. It's not often that we get someone as involved and as invested into a problem statement and a challenge as Dr. Chakravarthy has been with this. And it truly shines, and it showed here today. With all of the solutions that you presented, we could see the 8 months of hard work and longer for some of your existing solutions that you've tailored to meet this challenge needs. We really do appreciate all of your effort and time that you've put in for the last 8 months. Congratulations to Aeronaculus and your winning team today. But really, we want to just thank all of the finalists here. We recognize the tremendous efforts that you've put in and the great solutions that you've proposed to us. Just some other housekeeping things. If you want to learn more about some of the solutions that were presented here today, please feel free to check them out on the Expo Hall online. You can see more about the teams that presented and their solutions, and that will be available on the Ensign website. For those of us here in person, please join us for a networking and reception following this, beginning, I think, just shortly after this. So thank you.